We now discuss another problem in which exact solution is available by making certain assumptions and of the boundary conditions, and also a problem or fluid flow situation that exists in real nature and is of interest for scientists and mathematicians. And the problem is known as motion produced due to a vortex filament. As we discuss the effects of the rotation and rotationary effects, now let us consider the flow of a viscous fluid produced by a vortex filament in a fluid at rest. Now the streamlines and then the concentric circles with their center on the vortex filament. The velocity field is purely circumferential and varies with distance r from the center. The equations of motion, they can be set to be of this form, because if we consider the vortex filament, then the vortex filament for which the geometry determines that the fluid flow looks like this, the only motion that occurs is in the angular direction and not in a radial or vertical direction. Therefore, the velocity components u of r and u of z, that is velocity component in r direction, radial direction or vertical direction, are 0, and u of phi, that is the velocity component in the phi direction, angular direction, is, we can denote it by v depending upon r and time t. So the equation of motion then are reduced to, of course we mean the Navier-Stokes equation, they are reduced to dp by dr, the partial derivative, equal to rho v square by r, and the partial derivative of velocity v divided by derivative of t, the partial derivative, equals nu, the kinematic viscosity, times second derivative of v with respect to second derivative of time, so d2 by dt2 plus 1 by r into dv by dr minus v over r square. So this is also v over r square. The term for the pressure dp by d phi is 0. That means no variation of pressure in the angular direction. And because if it is not 0, then it is not possible to maintain the circumferential flow that is occurring, that is in the vortex filament. For a non-viscous fluid, the vortex filament is preserved indefinitely, and the velocity field given by v is equal to gamma infinity, capital gamma, divided by 2 pi r, where the gamma is the constant circulation of the vortex filament. You will be familiar that gamma is, normally we denote circulation by gamma. In the case of a viscous fluid, because of the internal friction, a continuous supply of energy is indeed essential to maintain the vortex filament. Otherwise, it will vanish with time. Then we consider the motion produced by a vortex filament starting from time t equal to 0. And in this case, the equation, because of from here, is reduced to, this is the term that we denote for vorticity, and by omega we denote the vorticity component or the effect of vorticity in terms of the velocity v, and therefore equation number 33 reduced to equation this, with the boundary condition that omega is equal to 0 when time is 0 for all radii. So within the vortex filament, this is the condition for vorticity, for the angular velocity, and this tends to 0 for large values of r. So you remember that this reflects to initial term, and this reflects to when the motion has taken effect, when time is also not 0, greater than 0. The solution of equation 35, which was given above, then by using this condition, we can take to be as this, because as we know, that equation, partial differential equation, is a well-known equation, and its solution is found to be in the form of diffusion equation. So the result or the solution can be taken to be this. If we substitute it back, you will see that it will satisfy the equation identically. Obviously, this is a familiar equation in partial differential equations. We have come across with this solution a number of times. Now the question is to determine alpha or alpha naught, and its value is obtained to be gamma over 4 pi nu when we substitute it back into the equations and make use of the boundary conditions, that the velocity and the vorticity are given by, so this is the velocity component and this is the vorticity, the two are given by this, so we obtain the fluid flow that is produced by vortex filament. And from equation, when the time is we find that at time t the flow is irrotational, but for t greater than 0 the vorticity decays, because as r increases we can see that this term will decrease because it has a minus sign, e to the power minus, so it means the function's value will be decaying, and finally its value will turn out to be, vorticity will take the value of beta naught over t square into 1 minus r square over 4 nu t e to the power r square by 4 nu t with a negative sign. So again that shows that when r increases, this function is going to decrease, if for a small t of course, and the same is as far as the velocity this is concerned, its value will be, so the function will be acting as given. Now if the total angular momentum of the fluid in the region is rho into lambda, then using rho into lambda to be this total integral, because it has taken care of the integral over all the variation of theta, which varies from 0 to pi, and the r varies from 0 to infinity, and the value of beta naught is obtained to be this quantity. As you can see, you can satisfy yourself that this solution, this equation is identically satisfied.